talk. So please go ahead.
All right, great. So hi, everyone. My name is Gianantonio Pezzullo. And in this presentation, I'm going to talk about the track finder algorithm for the trigger system of the Mu2e experiment at Fermi. So first of all, let me shortly introduce the physics of the experiment. So Mu2e will be looking for the muon conversion, which is the process where a muon converts into an electron in the field of an aluminum nucleus, in this case. So in this process has the same dynamic of the a two-body decay, which results in a monochromatic electron with an energy which is slightly below the muon rest mass. And because there are several advantages from the experimental point of view and also from the theoretical point of view, we usually normalize the rate of this process with respect to the muon capture process. So this process, as you may know, is a charge electron favor ballooning process. So it's forbidden in the standard model. And even if we extend the standard model, including the neutrino masses and mixing, the rate at which this process is predicted is fairly negligible, at the level 10 to the minus 52. But what is actually pretty interesting is the fact that many physics models beyond the standard model, which actually predict the rate of the muon conversion at levels that would be actually achievable by the future facilities around the world, like in the SUSY case or leptocore case. So that's actually really appealing for us for investigating the measurement of this process. So here on slide number 5, you can actually see a chart with the history of the limits that have been actually imposed on the charge electron favor ballooning processes in the muon sector. So here you can actually notice these green squares, which represent the current limit on the muon conversion set by the syndrome 2 experiment at the level of about 10 to the minus 13. And here on the bottom right, you can see the two experiments, Mu2e and its competitor, the COMET experiment in Japan, which aim to set a limit on the sensitivity at the level of 10 to the minus 17. So 4 orders of magnitude in improvement, expected improvement. So let's now go and have a look at the detector apparatus of the experiment. So Mu2e consists of 3 main superconducting solenoids. The first is the so-called production solenoid, where we essentially fire a AGV proton beam into a tungsten target, producing mostly pions. Then, thanks to a graded magnetic field, we actually focus all the charged pions towards the second solenoid, where that has this S shape and is named the transport solenoid, where we perform a selection of charge and momentum for selecting only negative muons that are allowed then to reach the final solenoid, which is named the detector solenoid. Here, the muon beam strikes a stopping target, an aluminum stopping target, where we create muonic atoms. So here, once the muon is stopped, it quickly falls to the 1s state of the nucleus. And what it can do are essentially these 3 main processes. So it can either decay through the standard initial decay, but is in orbit. So the dynamic is different. And that represents one of the most important background for the experiment. It can also do capture, and as I said before, this is usually a normalization process, but it actually creates a lot of noise in the detector because a lot of particles are produced, protons, neutrons, tritium, and photons, and neutrons. And then there's the conversion that currently has a limit of 10 to the minus 13, but we aim to observe something, hopefully, at a much lower rate. So downstream to the stopping target, we have a tracking system that we'll be discussing shortly, and then an electromagnetic calorimeter that is built with the cesium iodide crystals. So let's now see how the background has been driving the design of the experimental apparatus. So as I said before, the muon decay in orbit processes are one of the most important background for us. And this is the plot representing, showing why this is so important for us. So this plot in the slide represents the energy spectrum of the resulting electron coming out of this process. So here you can actually notice that it's not like the Michel decay, where we have a muon decay at rest and there is a sharp edge at 52.8 MeV, but here, because of the presence of the nucleus, the dynamic is completely different. And then we have 3 main features in this spectrum. First of all, the endpoint coincides exactly with the conversion electron energy, as you can see from the zoomed endpoint in the right side of the slide. And then you can see that the spectrum is actually falling pretty steeply as the 5th power of delta E. And then the third important point is the fact that about 10 to the minus 17th of the spectrum is within the last 1 MeV, closer to the endpoint. So it's really important for us to design a tracking system which will be capable for us to distinguish the two contributions from the decay orbit electrons and the signal electrons. So here in this slide, you can see the tracker design that that we came up with. So it's a very long tracker. It's about 3.2 meters in length, and it's made out of 36 equally spaced planes, tracking planes, which are made of 6 panels. And a single panel is essentially shown here by this picture on the bottom left. It's made out of 96 staggered straw tubes, and each straw tube has a variable length from 20 centimeters up to about 1.2 meters, and it's filled with a gas mixture of argon CO2. And a very important feature of this tracker is this hollow in the middle, because we actually left the inner 38 centimeters uninstrumented on purpose, because in this way we will be blind to all the incoming low energy particles, mostly decay in orbit electrons that are producing the stopping target, and will be just moving downstream inside the tracker without producing any hits in the detector. So then you have also another list of other backgrounds that I will be not talking about today, but I have a few backup slides if you're interested in knowing all these other backgrounds, but they were out of the topic of this talk. So now let's move to discuss the trigger system of the experiment. So here on this slide, you can see on the right side a picture representing the architecture that we're going to use. So essentially, we will be doing a continuous stream of the data from the readout controllers, which are sitting together inside the detector solenoid on the sides of both detectors, the tracker and the calorimeter. And we'll be streaming out this data to the data transfer controller units, the DTCs, and then we will collect all the event slices into a single DTC unit using a 10 gigabit switch. And what we will do once we collect all the data into a single DTC, we will run online reconstruction of the event, and we will also run together the trigger filters on these reconstructed data. And if an event gets accepted, we will also pull the information from other sub-detectors, which I didn't present, are essentially the cosmic ray video and other monitoring detectors, which are located outside the detector solenoid. So the requirements of this trigger system are listed below on the slide. So we require the trigger rate to be below a few kilohertz, which is equivalent to ask for a maximum of 7 petabytes per year in the data volume. And we also enforce a requirement on the processing time given by the hardware that we actually have available for implementing this trigger facility. And it's going to be a limit on the processing time of about 5 milliseconds per event. So now let's see how we implement the online track finder algorithm in the experiment. So we factorized the track search into 4 main stages. In the first one, we essentially prepare the hits by reconstructing them. So we combine the information that we have from the electronics on both sides of the straw tubes in order to reconstruct for each straw tube a given hit time and position along the wire. And then what we do is combining the JSON straw hits within the same panel in order to create a so-called panel hit. And that has essentially 2 benefits. So first, we improve the resolution along the wire, which is important for the pattern recognition. And then we also reduce the amount of hits to be processed by the pattern recognition. So we reduce all the combinatorics, which is important for matching the timing constraints that we have. And secondly, once we have all these panel hits, we try to identify the group of panel hits which is compatible with being produced by a low momentum compton electrons that are produced inside the tracker. And this is fairly important because once we flag these hits, these are not used in the pattern recognition stage, which is the next stage. And in this way, we avoid eventual confusion that these low energy electrons may create inside the chamber. So then, and for the pattern recognition, we actually use 2 different algorithms. One is so-called a track path rec, and is essentially an iterative procedure that uses triplets to derive the circle part in the transverse plane, XY. And then we also perform the other reconstruction of the helix in the phi z plane, where phi here identifies just the angular coordinate of a given hit with respect to the helix main axis. And in the other algorithm is instead a calorimeter seeded algorithm, which enforces the calorimeter information to select the cluster of panel hits to be processed, and then performs chi-square based fits on both the transverse plane and in the phi z plane to reconstruct the helix parameters. So let's now discuss about track path rec. So in the first stage of the pattern recognition, we need to select the cluster of hits to be actually processed for searching for a given helix. So what we use is an MBA-based algorithm, which is essentially identifies peaks in the distribution of the panel hits time. And in order to improve the accuracy of this process, what we do is essentially we convert the hit time into an extrapolated hit time at a given plane, for convenience that z equals 0, which is the middle of the tracker. And in doing this extrapolation, we essentially are assuming a beta equal to 1, which is a good assumption for the conversion electron, because at above 20 MeV, an electron is already super relativistic. So at 100 MeV, beta equal to 1 is a good assumption. And we also are assuming a given pitch angle for the track to be the average value that we expect for the conversion electron. And this actually allows us to factorize out the propagation time, and with respect to the width given by the timing resolution of a given panel hit. So is that actually pretty useful in the reducing the width of this peak that we are looking for in the distribution. Then we start the real pattern recognition. So what we do, we divide the pattern recognition into 2 different steps. So first, we look for circles into the transverse plane. And then, as I said, we look essentially for a line, because it's a linear relation between the phi and z. And in implementing these 2 parts, we actually do some annealing procedure, and we perform some heat cleanup, migrating from one step to another. In this way, we get rid of eventual outliers that could be still present into the cluster of hits that we are processing. So for the XY circle reconstruction, what we do, we essentially loop over all the possible triplets of panel hits, and we select the triplets in a way that a given panel, we don't have more than 1 panel hit for a given tracking plane. And using a given triplet, if it covers a sufficient area, we actually perform the extrapolation of the x0 and y0 coordinates, which are the center, which are the coordinates of the helix center into the transverse plane, using just the intersect of the 2 perpendicular bisectors. So it's pretty straightforward. And then once we do this operation with all the possible triplets that we can make, we just use the median operation to derive the most reasonable values for x0 and y0. And once we have the coordinates of the center, we repeat another loop among all the hits, the panel hits, to derive the best estimate of the radius. And also in this case, we use the median, because we turned out to be the most stable operation for retrieving the most accurate result. Then we have the second stage, which is the phi-z line reconstruction. And here we need to notice the fact that our expected conversion electron tracks will have multiple loops in the chamber, as is shown here by this plot in the bottom left side. So in order to perform this phi-z reconstruction, we need first to resolve the so-called 2-pi ambiguity, which means that for each given hit that has a given phi with respect to the helix axis, we need to take into account the factor 2-pi for each loop that the particle made. So to do that, we essentially use an histogramming procedure. So first, we create a histogram of this quantity, which is shown here in the third bullet of the slide. So we essentially are testing, adding this factor 2-pi k to each phi. We are essentially testing all the possible cases. So for a given phi to be in the kth loop. And once we finish creating this histogram, taking all the possible pairs of hits, what we do is essentially taking the peak of this distribution as first approximation of the slope that we try to reconstruct. And then once we have this 2-pi ambiguity resolved for all the phis, we repeat the histogramming procedure, but without taking into account this factor of 2-pi k, because we corrected the 2-pi ambiguity. And so we have the situation which is represented by the bottom right picture. So where we essentially corrected the 2-pi ambiguity for all the hits, so they identify a pretty straightforward way a line, and then we essentially just repeat the histogramming procedure, which much finer binning, in order to identify the peak, which is going to represent the most accurate reconstruction of lambda for our helix. So we tested the performance of this algorithm using a sample of conversion electrons overlaid with expected background that comes out essentially from all the beam-induced processes with the stopping target, and also with the muon capture events that I talked about before. So the resulting distribution in the bottom left shows the momentum distribution we get at the pattern recognition stage. So here you can see the peak is pretty close to 100 MeV/c, and the plot on the right shows instead the resolution, the momentum resolution that is expected out of the pattern recognition stage, which is at a level of 4%. Other interesting distribution are shown here on slide number 26. So on the left, you can see that we have an average of 34 straw hits associated with the reconstructed helices. And on the middle and on the right, I create this distribution of the chi-squares, which is not really, well, it's actually just indicative of the purity, not only purity, but like of the quality of the reconstruction that we make, even if we actually don't reduce any chi-square in performing the circle or the line reconstruction. But still, that distribution is good enough that it shows essentially that the reconstruction is proceeding well. Moving to the second algorithm, the calorimeter seeded algorithm. So here, what we do for selecting the cluster of hits to be processed, we enforce essentially time gate with the calorimeter cluster time with a width of about 80 nanoseconds. And then we use also the spatial correlation to identify just half semi-plane, as it's shown here by this illustration in the bottom of the slide. So we are actually capable to select just half of the semi-transverse plane where to look for the hits, and that combined with the time gate, it gives actually pretty good selection of the hits to be processed for setting for a helix. Then the pattern recognition is actually is implemented like in a 3D way. So what we do is illustrated here in this slide. So we start with a triplet, which is made out of the calorimeter cluster position, one panel hit, and we start with the one closer to the stopping target, a lower Z, and then the solenoid center, because this algorithm is tailored for reconstructing only for helices coming out of the solenoid or out of the stopping target, which is located exactly in the center of this transverse plane. So what we do, we evaluate the helix parameters using this triplet, and we obtain this dashed line represented in the picture. And then what we do, we extrapolate the helix into the next tracking plane, and we pick all the hits which are within the code that we use for implementing this extrapolation. And as soon as we have a second panel hit that is added into our bucket, we reevaluate the helix parameters. And what we do, we essentially correct the helix parameters and we start the procedure, and we keep on going essentially by adding all the hits that we find by extrapolating the helix into all the tracking planes up to the end. And also in this case, we perform a study of the expected performance using the same sample that I explained before, and the results are shown by these two distributions in the bottom of the slide. So you can see the momentum distribution in the bottom left, and here actually we can notice that it peaks much closer to 105 MeV, and in the bottom right you can actually see that the expected momentum distribution that we achieve is slightly better than the previous algorithm, so it's at the level of 3%. So here, these are the other distributions showing some interesting results. So we also have an average number of 34 straw hits for this algorithm. And here, the chi-square distributions actually are more meaningful because we do reduce a chi-square for performing both the circle fit and the line fit. So here you can see that from the shape of the chi-square distributions that actually we obtain pretty good results, and we have a quite good understanding of the expected uncertainties of the panel hits that we use for performing these fits. So after the pattern recognition, what we do for both independently for both reconstruction lines is essentially a global chi-square fit of the hits that we clustered. So this is a chi-square fit through the hit wires, where we do not resolve any left-right ambiguity of the hits, because that would take too much time. And also we do not apply the common filter correction, because also that would take a lot of time that we don't have available at the online reconstruction level. So you can see the results in the bottom side of the slides here. On the left, the resulting momentum distribution, and on the right, the expected momentum resolution, also in this case evaluated for the same sample of conversion electron overlaid with the expected background. And here you can notice that expected momentum resolution is pretty good. It's at a level of 1.4%, which still for the online reconstruction is pretty good. And here are the interesting distributions. So on the left, the usual distribution of the expected number of straw hits collected within this track, and it's still this at 34, so we didn't lose any hits on average. And on the right, this is an interesting distribution which shows the purity of the cluster of hits that we actually collected. So this is just the ratio of the number of straw hits correctly assigned to the track and divided by the total number of hits that have been collected at this stage. And you can see that the average is about 95%, but you have also this big spike at 1, which means just essentially pure sample of hits correctly assigned to the track. So the way we implement the track trigger is essentially by implementing this online reconstruction that I just described, but where we essentially add a filter at each stage of the reconstruction. So after the time clustering, after the path recognition, and after the track seed. So at each of these stages, we essentially have a filter configured. And the nice thing about our framework is that we actually can instantiate multiple track trigger lines with different configurations of the filters. And that would, the framework that we use allows us to actually do not run multiple times the reconstruction modules if they don't have different configurations, of course. But we can have multiple track trigger lines with filters set in different ways, but using the same reconstruction modules. And we know that the reconstruction modules would not run twice. So we evaluated the expected physics performance of these track triggers, and then we essentially evaluated that for this signal that I've been discussing, which is the conversion electron. And by using the OR of these two algorithms, we expect to achieve a trigger efficiency at the level of 98%. And we also evaluated the expected trigger efficiency for another signal that I didn't have time to discuss about, but I have a backup slide if you're interested, and is essentially a conversion positron with the momentum at about 92 MeV over C. And here, trigger efficiency is slightly lower, but still it's great. It's 96%. So yeah, it's above the actually requirement that we have. So we also evaluated the expected rejection of the track triggers. And to do that, we just use a pure sample of mixed background sources that we expect. And by simulating these backgrounds, we also fluctuated the proton bunch intensity using the best guess that we currently have. And this is the plot on the bottom left shows essentially the distribution of the proton bunch intensity that we expect to receive from the proton driver at Framelab. And the plot on the right here shows how the expected rejection varies as a function of the proton bunch intensity. So essentially evaluated the expected rejection at different working points. So one is just the nominal working point, and we essentially we plan to obtain something like 2000 as a rejection factor at this nominal condition, while as a benchmark, you can just take the point at 2. So when the beam intensity is twice as the expected one, and here the rejection is still at the level of 650, which is pretty good and above our requirement. So it's great. Then we also evaluated expected track trigger rates. And here I did this estimate for the on-speed condition, which means essentially for the condition where we actually are shooting the beam, because we will not receive a continuous beam. Map A is a pulsed beam, and the duty cycle is not 100% because we are going to share the beam with other experiments at Framelab. So our duty cycle is about 30%. And here, this table in the bottom of the slide shows the instantaneous rate when we receive the beam. So that's the thing that I estimated. So from this table, you can actually see that the expected rate of fake events, so where there was just some tracks got misreconstructed, that passed above, went above all the thresholds we impose, it's a level of few tens of hertz. Then we have a fairly large rate of these electrons from the decay in orbit processes as happening in the stopping target. Then I also put it here in the table because it's actually pretty interesting. These are essentially the decay in orbit electrons, which are produced not in the stopping target, but in a cylinder which has a much larger radius and is this proton absorber, which is in between the stopping target and the tracker. And it is an interesting source that we are going to use in the experiment for calibration and monitoring the beam, and I have a backup slide for that if you are interested. But this rate can be essentially tuned between a few hertz up to 6 kilohertz. So it's I just put it here as information. And so the expected total rate, instantaneous rate, is at a level of 700 hertz. So that's fairly below the few kilohertz that I said before as a requirement. We also tested the timing performance using the official software that we plan to use in the experiment in the real life. So we actually set up this prototype at of a data acquisition server at the Framelab Feynman Computing Center. And we started customizing this software off the shelves that has been developed by a group at Framelab. It's named OTS. And the results of this timing test is showed by these two plots in the bottom of the slide. So on the bottom left, you can actually see the expected timing of each of these modules that we will run. And I just use these colored squares to separate the modules using by the different algorithms and for doing the shared part, which is this heat preparation and filtering. And the plot on the right is pretty interesting because it shows the expected total time for the online reconstruction and triggering is it on the number of processes we're going to run on a single server. So starting from 1 up to 20, which is the number that we actually want to use. So we would like to run 20 event builders on a given server unit. And the result that we obtain is at the level of 6.5 milliseconds, which is above the requirement. And we know that. And we actually, I can tell you, already had planned studies for improving that. And we actually already squeezed it down, kind of close to the 5 milliseconds, but I didn't have time to actually put in a clean slide all the results that we achieved so far. But we have other mitigation strategies as well, like doing a pre-filtering of the hits using the calorimeter information, and that will reduce the total time at 20 cores below this 5 millisecond line, moving that to between 3.5 and 4. So that will slightly reduce the trigger efficiencies, but still will allow us to achieve 90% trigger efficiency and match the timing requirement. But we're trying to improve the timing of these modules, just improving handles and essentially the code. So as a summary, so Mu2e goal is to improve the sensitivity on the Mu conversion by 4 orders of magnitude, and our trigger system is based on 2 online pattern recognition algorithms. One that uses the calorimeter information for seeding the pattern recognition and is tailored for electrons coming from the stopping target, and the other one is instead a more general helix finder algorithm that uses no assumptions for the particle origin, and is also really necessary for achieving high performance in terms of trigger efficiency for the signal. So I showed you that the expected momentum resolution at the level of the pattern recognition for both algorithms is in between 3 and 4%, which is pretty good for a pattern recognition algorithm. And the total rejection is expected to be at a level of 2000 at nominal condition, and the trigger efficiency is at the level of 98% for the main signal that we would be looking for. I also showed the preliminary results for the timing test that we did with a real prototype of the TDAC system, and these showed a 6.5 millisecond of processing time per event, which is above our requirement threshold, but we already have good handles and studies ongoing for improving it. Thank you.
All right, thank you very much for this very detailed and very nice overview. We have time for a few questions because you were actually perfectly on time, given we started a little bit late. I had one question. Did you hear my little ding ding, or was that?
I actually didn't.
Okay. Did anybody else hear this, or was it just not loud enough? I can.
Yeah, no, I did not hear it.
No, Mattia.
Probably you can use it like an emoji, and that will show up in my screen.
Okay. So maybe I need to find a more disturbing noise for the next talk if it happens. All right. Let's start with the questions. If anybody wants to raise a hand or also just speak up if it is more or less quiet, I think we can try that as well. If nobody starts, I will have, I have 2 small questions. One, I wanted to ask about the panel hits. I didn't fully understand that. If you want to go maybe back to the slide, or you can also just answer. So I understand it if we have 2 straw hits, but I guess you have more straws together and you can have them.
Oh, so
go ahead.
Thanks for this question. Yeah, this is pretty interesting. So we actually use a time gate, okay? And thus, by using the time gate, if you will just look for JSON straws, the majority, we have, as I said, like multiple hits, but actually the occupancy is such that the average size of a panel hit that we combine is, I think, something like 85% of the time is like 2 hits, as I showed in this picture. And then we have a few with 3 hits. And the rate of actually wrong panel hits, where we combine straw hits made from different particles, is really low, is something like 1%. And that happens if there is like this one of the component electrons which is on time with the hits made by a real particle. But by using a time gate essentially, and just clustering JSON straws, so straws which are really adjacent to each other, it's a pretty good operation for reducing the amount of for reducing combinatorics essentially, and also improving the resolution along the wire. So it's
okay.
It's yeah, it doesn't create confusion for the pattern recognition essentially. So the probability to mix straw hits by different particles is extremely low.
And if you have 3 in a row, you still pick only 2 hits to be a panel?
No,
hit?
we combine all of 3. So
okay, so that one I didn't understand. It sounds
Here I just showed the most probable case where we have really only 2 hits.
Okay.
But there are cases also when we have just 1, or up to 3 or 4 actually. I think 4 is the largest one where we have in some weird configurations. Sometimes we have also 4, but it's something like in the 2% of the cases. So it's extremely rare.
Okay, well, that makes sense. And then I had only a small question on slide 33. You show on the plot on the right, I think, a really nice resolution.
Oh yeah.
I just had a question. Are you, maybe are you slightly worried, or do you also understand the shift in the mean? Like,
Thanks for this question. So we understand that. So the shift of the mean is because here I'm comparing the reconstructed momentum with the Monte Carlo value at the entrance of the tracker. And since we are not applying any Kalman filter correction, so when we perform this chi-square fit is a fit of a track with constant momentum in the tracker, because we don't know any Kalman filtering, nor we actually resolve the left-right ambiguity. So we expect to have that shift because we are essentially underestimating the momentum at the entrance of the tracker, because as we're doing essentially like getting a sort of an average momentum, we're not taking into account the energy losses in the tracker, which are at the level of like 1 MeV-ish, I think. And once we do the Kalman filtering, probably had a plot on the backup slide, and when I have a Kalman filtering and left-right ambiguity resolved, this distribution is perfectly peaking at 0.
Perfect. All right, thank you.
Okay.
Does maybe have time for one more question, if anybody has a follow-up question? Don't be shy, we can't even see you. All right, if not, thanks again for the very interesting talk.
Thank you.
And we will continue with the second